Good day, everyone. I'm Siti Asha, and today I'll be introducing our project on designing a flash separation system for ethane-propane mixture. Flash separation is a simple and economical process used to separate components in a mixture based on different volatility. The mixture of ethane and propane we are working with is a common byproduct in the natural gas processing and petroleum refining. Ethane and propane are valuable hydrocarbons in various industrial applications. Efficient separation of the component enhance their value and also purity. In the flash drum, the feed mixture enter due to the specific temperature and pressure condition, it's partially vaporized. This vaporization allow the more volatile component, which is ethane, to be separate from the less volatile propane. So our goal is to design an optimal flash separation process that maximize the yield and purity of both ethane and propane. So, making the process more cost effective and beneficial for industrial application.
Hi, my name is Ethane and I'm going to talk about process and composition condition. Process, we use flash separation, also known as a flash evaporations. It is a straightforward separation process used to separate component in a liquid stream. The operation of the flash separation involves reducing the pressure of the liquid vapor mixture rapidly. The flash vaporization is used in the industry such as oil and gas, chemical, and petrochemical. Step 1 is the initial mixture. You start with a liquid stream containing both propane and ethane. Step 2 is a flash drum. The mixture is partially vaporized in a flash drum at a specific pressure and temperature. This results in two bases. First, vapor base, enriched in the more volatile components such as ethane, and second is a liquid phase, enriched in the less volatile components such as propane. For the last step, which is step 3, is separations. The vapor phase and liquid phase are then separated, allowing you to obtain purified propane and ethane stream. For the composition condition, first, temperature and pressure control. The mixture must be brought to a specific temperature and pressure where a portion of the mixture will vaporize, while the rest remain in the liquid forms. The chosen conditions should allow a significant difference in the vapor-liquid equilibrium of propane and ethane. Second, feed compositions. The composition of the feed mixture should be known as it affects the equilibrium conditions and the efficiency of the separations. And lastly is phase separation efficiency. The design of the flash separator must ensure efficient separation of the vapor and liquid phase. This typically involves proper sizings and internals, such as the mixer pads or trays to minimize entrainment of liquid in the vapor phase.
Here is the example flux calculation step where the system is carried out at 298.15 Kelvin and 5000 kilopascal. In this experiment, the mole fraction of the ethane is 0.9, methane is 0.07, and propane is 0.03. Before we finding the mole fraction of the liquid and vapor phase, we calculate the vapor fraction of each species I first. So equation of calculation of the P saturated is ln P equals to C1 plus C2 over T plus C3 ln T plus C4 T to the power of C5. Next, we start of P bubble calculation. Assuming the composition of species I equals to mole fraction of liquid of species I. At bubble point, it contains 1 mole of liquid but 0 mole of vapor. P bubble equals to the summation of the mole fraction of liquid of species I times P saturated of species I, and we will get 8128 kilopascal. Same goes to P due calculation. For the P due calculation, assuming the composition of species I equals to the mole fraction of vapor of species I. At dew point, it contains 0 mole of liquid but 1 mole of vapor. P dew equals to 1 over summation of mole fraction of vapor over P saturated of species I, and we will get 4039.9 kilopascal. Since the P due smaller than the P system and P bubble smaller than the P system, hence the system is not in two-phase region. Then proceed to K value calculation. K of the species I equals to P saturated of species I over P system. Then, based on the vapor-liquid equilibrium, the action V should be below 1.0 as the sum of the mole of the vapor and liquid is equals to 1 and is by using try and error method. For the mole fraction of vapor and liquid calculation, we first try using V equals to zero point 0.5 for the first iteration. So at V equals to zero point 0.5, summation of Y of species I is 0.9595 and X is 1.0405. Next, we try for the second iteration by using mole of the vapor equals to 0.291343 and the summation of Y of species I is 0.9995 and X is 1.0002 and the mole fraction of vapor and liquid is more consistent at V equals to 0.291343 compared to that of vapor equals to zero point 0.5. So therefore the mole of the vapor equals to 0.291343 where the mole of the liquid is 1 minus V equals to 0.708657.
I will continue with the flash calculation comparison with different brushes. The others use 5,300, 600 kPa to carry out the experiment where we also added additional 9,000 kPa for the compression purpose. So for a system to be in two-phase equilibrium, the system should fulfill the condition where P system should lie in between P due and P bubble. After the calculation, we can see that Weber mole calculation went wrong when B system is larger than B bubble, especially for the case of B system is 300 kPa. The same situation can be seen when B system is 9,000 kPa, whereby B system has larger value than that of B due, leading to incorrect liquid mole calculation. To sum up, 5,000 kPa is selected as the pressure system. If you can see from the table over here, the green color box, it fulfills the condition where P system is larger than P due and also it is smaller than P bubble. And then you can see also the V, L, Yi, and Xi values are reliable, whereby they are all below than 1, and also the total up of V plus L is 1, and then the total up for both Xi and Yi value will be 1 as well. So in terms of separation using flash calculation and also by assuming the validity of Rao's law, the flash separation when using P system as 5,000 kPa is possible. And last but not least, there is another key point from the comparison that we can see is that the pressure play the critical role for flash separation.
So lastly, for conclusion, our project aim to maximize yield and purity through precise calculation of a preset temperature, pressure, and also overall composition. This effort ensure efficiency and also compliance with industry standards. So, looking ahead, further enhancement promise increased efficiency and also economic benefit across industry. Our focus on efficient separation technique, including calculating moles of vapor versus mole of liquid, underscore our commitment to industry advancement. So, calculating preset temperature and pressure, understanding the overall composition of the feed mixture, and also measuring the moles of vapor against the moles of liquid are all important factors optimize this process. So, looking ahead, we has underscore our commitment to industry advancement. So, thank you for your attention, everyone.